Hello everyone. Again, ECE100, class number 4. In this class, we're gonna talk about resistance and Ohm's law. So before we do that, let's talk about one of the fundamental equipment or device we use in our lab to test any circuit very quickly. That is breadboard. There's a handout I gave you in the class, a previous class, to go through that how breadboard works, and also you learned about breadboard in maybe high school in EPADS, also physics 260. So you use them somewhere there. So let me remind you what is the key things about the breadboard. In the breadboard, you have these 5 connection point here. We call them node. So that means these 5 points, basically a single point, they're connected to each other. So if you make connection in any of the 5 points, you're making connection with the same point. These are called nodes. And also over here, I'm going to take 2 different color here. Let me try to get a red one here. So red one is positive. Let me see which side is positive. I cannot see which side is positive. Let's assume that this side is positive here. So this, the bottom one here, if this is positive, that whole rail is connected together. We call them bus. And if the top one is negative, I'm going to assume top one is negative. I'm going to do it with a black one here. So they're all connected together. These are called bus. That means we use the bus to make the power connection or a reference connection. So we normally use the negative one for the reference connection and positive one for the positive voltage connection. So you have this basically has 2 breadboard here. So this one is one breadboard here. This one is another breadboard over here. So that both breadboard has 2 buses, right? 2 buses on here. This is one bus. This is another bus over here, and they're all connected together. This line is connected all the way from left to right here, and this line also connected from all the left to right here. But there's no connection between these 2 lines, and also there is no connection between side by side here. So there is no connection between side by side here. So that means we use this middle part here. We use this middle part over here to make a circuit connection, and we use the 2 sides with the bus to basically bring the power to the circuit board. And to make the connection for this particular circuit over here in the breadboard, so I have 5 volts coming in. So I assume that my power supply is supplying 5 volt here, so I can bring this positive supply to here, and my negative can go to the reference here. So then I can connect from here to, let's say this side is positive over here, and I can connect this one to this side over here. So I connected 2 different points here. That means this whole rail now has 5 volts, and this whole rail over here has a reference over here. So now to make connection, let me get the, so make connection here. So these are the connection point right here. This is the same point over here. This is the same point over here, and all the way, this is all the same point over here. So I can connect this whole node over here to the reference, which is the negative side, and one end of the 500 volt will be connected to the positive side. So my positive is, let me go back and redo the positive here. So let's do the redo the positive here. So positive, let's do the red one for the positive. So that's positive here, that's positive over here, then black one for the negative. So bring it negative over here. So now let's say that I'm gonna connect, I'm gonna take the blue one for component now. So let's say that I'm gonna connect this is my 500 ohms here. So this end should connect to the positive. I'm gonna use let's say I'm gonna use again blue for all the connection here. So this end needs to connect to the positive, so that there's a wire goes from positive bus to that node over here. And this one here, I have 2 more. This node, I have 2 more 1K connection here. So I'm gonna use this one here for 1K. I'm going to use this one here, another 1K. So bring in 2 here. So this is 1 kilo ohms, this is 1 kilo ohms. Look at that here. So this node is same as this node here. I'm going to mark it number 2, number 2. And this node over here is number 1. This is number 1 here. Then all of them here, this number 3 node here would be this node over here. So I need another wire to go from this node to the reference, which is negative right here. So that is your number 3 node right here. So can you see that now how this circuit came from the schematic to the breadboard? All right. So that's how you basically do breadboard connection using circuit diagram, and you basically go from node to node to do that. So that's the same circuit, not the same circuit, different circuit here. I have to show you what is the good breadboard practice. So this breadboard practice is very good. It's clean. Use minimum number of wires and trimmed all those components to the right length so that stick into the breadboard very nicely. And also, if you look at here, the both side has the power, both side has the power. And both side also have the reference. So this whole rail over here is a positive voltage. This is the positive voltage here. This is the negative voltage over here, or reference. And on this side, positive voltage here, reference here. And also we made connection from here to here. So this rail also has the reference now, and this rail also has the positive voltage. And same here, this rail has the reference, and this is the positive voltage. So that means this whole breadboard on all 4 buses has the power supply now, and you can make circuit anywhere you want. This is a very good practice. Nothing is jumping, nothing is making loop on the breadboard. Very nicely laid on the breadboard. This one is acceptable, and you can see that these wires are not cut in the right length, and also there's a excess wire here. You don't have to have that over there, and that's still acceptable. But this one is not acceptable. This breadboard planning taking too much space and too many wires, and the resistor was not trimmed. So this is a very bad practice for breadboard connection. Let's look at the resistance. Resistance is the fixed property of the device. That means if we apply electrically fixed property of the device means that resistance has this equation over here, L over A. You have seen that before. So that depends on length, cross-section area, and the resistivity rho. So this is a fixed for a fixed device, and we can measure the resistance by using voltage and current. So ratio is voltage to current. So V is R is V over I. So if you know how much voltage across that resistance and how much current going through the device, I can find the resistance of the device. So this V is voltage across the device, and I, the current through the device. This is very important here. We're not talking about any other current. We're talking the current going through that particular device, and we're not talking about any other voltage. We're talking the voltage that's just across that device. So that's very important. So if we know voltage across the device, we know current through the device, we can easily find the resistance by finding the ratio of that. All right, and we're going to do this in the class with a practice problem here. So measure the resistance, very simple. We just go put a knob to the resistance measurement buttons, and basically put the 2 probe across the resistor. You'll find the resistance value on the meter. So Ohm's law. Ohm's law is let's see. Ohm's law is basically saying that your voltage and current, they're so V equal to IR. That means that your voltage and current, they're directly proportional to each other through a particular device. So V is directly proportional to I. All right. So, and if you take the ratio, if they take the ratio, or if you try to make this equal, V equal to I, there is a proportionality constant that is R. So R is the proportionality constant between them. So V equal to IR, right? So what does it mean? What does it mean for a device? The R is the proportionality constant. So it does not depend on applied voltage, magnitude, or polarity. So it's saying that resistance of a device is independent of applied voltage, magnitude, or polarity. So that means for a device to obey the Ohm's law, your resistance of the device, which is R, is independent of voltage, magnitude, and or polarity. All right. What does it mean? So if I draw something over here, let's say that this is your I, this is your voltage. If I have a linear relationship here, so that means your voltage going up, current going up, voltage going down, current going down. The slope, it does not depend on polarity of the voltage or the magnitude. Slope is always constant. So slope is constant, right? So that is the R. So R is V over I. Okay. So slope is constant. So that means this device obeys the Ohm's law. If I have something over here, something like that, right? So this is I, this is V, right? This one slope is not constant. So that means your slope is changing depending on voltage, polarity, magnitude. So that means slope is not constant. That means this device does not obey Ohm's law. This one obeys Ohm's law. So to obey the Ohm's law, your resistance value cannot be dependent on voltage, polarity, or magnitude. So mathematical form of Ohm's law, I showed you that this is basically V equal to IR. If temperature goes up, so T is going up, your R also goes up. This is normal for resistance, but for our class, we basically will neglect the temperature effect on the resistance. So what is the resistive circuit? Is basically a circuit only contains the resistance. So if I draw this over here, so you have R1, R2, R3, all are resistance. So that is basically a resistive circuit. Power equations and Ohm's law. So let's do it here. So Ohm's law is V equal to IR, right? And power equation is P equal to VI. So if I now, let's say V equal to IR, so if I put it back here, it should be IR times R, so it becomes I square R. So that is one equation for power. And if I do another one here, if I say I equal to, you can also say that over here, I equal to V over R. So if I do it over here, so V, I becomes V over R, should be V squared by R, V squared by R. So this is another equation for power. So power has three equations now. So P equal to VI, P equal to I squared R, P equal to V squared by R. So remember that we're trying to find power consumed by device or dissipated by device, you always look for the voltage across it and current through it, or voltage current through it and resistance of the device, or voltage across it, resistance of the device. So that means what I'm talking about here, if you're trying to find the power for this device, you always look for the voltage across it, the R of the device, and the current going through the device. You don't take the current and voltage and from different places and try to find the power of a particular device. So resistance has different tolerance, 10%, 5%, and 1%. Higher the tolerance, more accurate, but also more expensive. For our lab, we basically use 5% tolerance. So if we're looking for 100 ohms, it could be 95, could be 105, in between somewhere. And color coded, all resistance has some color code. Like for me, I'm colorblind, so I cannot read color code. So I always measure them with the multimeter. If you're very good at color code, you can use that, but color code is basically not universal for everyone. And also all resistance comes with the power ratings, like 100 ohms, would say half watt here. That means you cannot dissipate more than half watt through the resistors. If you do that, that's going to destroy it, you're going to burn it. Okay, so you have to power rating of the resistance is half watt, so your power dissipation through the resistor should be less than half watt. So we're going to solve this problem in the class, and we're going to do this in the class too. We're going to do this in the class also, and we're going to do this in the class also. And we're going to try to do it breadboard practice in the class if we have time. And that's all for today. I'll see you for class 5.